Thank you very much for the kind invitation and for having me come to IIT Roorkee, and I've really enjoyed my stay so far. It's a wonderful campus and a wonderful place to be. I do often come to India about between 1 and 3 times a year to work with Tibetan monks in the south of India and study how the practices they do affect their brain waves, their cognition and their mind. But I'm not going to talk about that right now. Here I'm talking a little bit about the other research I do, which is about how do we mind wander. You might all have had the experience that your mind sort of slowly drifts away when you're trying to write a paper or when you're attending a lecture. But how does that happen? Why does that happen? What happens in the brain when that occurs? And when is it maybe useful? When is it not? Those are the kind of questions that we're trying to answer in my lab. So I will share some of that work, and especially the computational modeling work, here being a visitor of the computer science department. Before I get into that, let me thank my collaborators. So this is Professor Tatgen, who is the head of our cognitive modeling group. And these are the students who are doing some of this work, without whom this would not be possible. So it's an assortment of master students and PhD students. So now let's get into it. What's mind wandering? It's typically in the psychology and neuroscience literature, this process is defined as task unrelated thoughts. So any thoughts that are unrelated to what you're currently doing. This might sometimes be positive because it might be negative when you're trying to write a paper and your mind sort of zooms off and you've lost your train of thought, or when you're attending a lecture you might have missed part of the lecture. But it can also have positive side effects. Sometimes it's been related to creativity, like mind wandering allows you to make maybe unexpected connections with things. So the question is really, when is it helpful, when is it not? And to answer that question, I think, and I'm fairly unique, I guess, in that, I think we need computational modeling. Most people in this field don't use computational modeling, they just look at people's behavior, but I think you need a strong computational theory to actually make good inferences about what mind wandering really is. And also I think we need neuroscience so we can track mind wandering in real time. So let me get started by first explaining a little bit what the logic is of computational modeling of cognition, because you might not be familiar with this. And this is basically the main thing we do in our research group that's centered around cognitive modeling. So we've made a little movie to explain how this works.
But also to understand brain diseases better, so we can help those suffering from brain disorders. Many scientists, our brains can support a whole variety. Studying French. How is that possible? That's what we're trying to find out. Not only to be able to build intelligent robots and computers who think just like we do, but also to understand brain diseases better, so we can help those suffering from brain disorders. Many scientists try to understand how brains work by studying how they react in different situations. We try to simulate the human brain. We build a computer model of how we think the brain works, and then we compare its performance to the performance of real brains. This way, we hope to understand how different brain parts work together. Your brain, for example, has a working memory, a kind of sketchpad for maintaining information temporarily. There is a visual part of the brain, where the images from your eyes arrive, and a place where sounds coming from your ears are processed. There is also a long-term memory, which remembers where you live and who you are, a part that moves your muscles, and there are several other parts, some of which we don't even know yet. But how do all these bits work together? What pieces are there? How do they work? How are they connected? We think you can figure that out by trying to build a copy. We program a computer to have a working memory just like in our own brains, and a long-term memory that forgets things at just the same rate as real human memory. fake brains. But first, we test the brains of actual people. For example, by having somebody drive the car and talk at the same time. This is possible, even though you do two things at once. But when somebody tries to text as well as drive, things are likely to go wrong. Why? Let's see what our computer brain does. In this model, the eyes are connected to the visual part of the brain, which is connected to working memory, just like the hearing part of the brain. It is possible to talk and look at the road at the same time, but if you're texting while driving, the visual brain has to route two streams of visual information to working memory, and that is impossible. If the computer model's performance matches real people's performance, then our model might be similar to how our brains really are. Often, our computer models can already predict which brain regions become more active. This way, we try to find out how the brain works. Try to build it like we think it is, and then check if that squares with our knowledge of the real brain. And if it doesn't, it's back to the drawing board.
Okay, so this is what we're trying to do. So let's apply this idea to a model of mind wandering. How would we put this together? Well, based on a whole bunch of neuroscience and psychological research, we came up with the idea that mind wandering is really like a competing task. So when you're writing your article, this mind wandering process is like another task that fights with your writing the paper task. And it consists mostly of retrieving memories. Because we often, we project, we simulate the future when we're mind wandering, or we might revisit the past. So it's really a lot of memory processes. And also we see, when somebody's mind wandering, we see brain areas related to memory being quite active. This is called the default mode network, which involves the medial temporal lobe, the hippocampus, which is really associated with memory retrievals. Now, one important thing to keep in mind is that really not all mind wandering is the same, as I'm going to explain in this talk. And this is important because, again, for this question of when is it useful, when is it not, I mean, one very clear case of where it's not useful is a little worse than when you're losing your attention, for example, in the driving the car scenario that was in the movie. Namely, it's the case of depressive rumination. So nowadays, more and more people get depressed, at least in the West, but I've heard that also in India this is an increasing problem. And people really suffer from these thought processes like, I'm worthless, I'm not contributing anything to the world, those kind of processes. And that really impairs their ability to function, and it becomes a big public health problem. So how does rumination work? Well, this is caused by a change in memory structure. So when we can model this, we actually found that we were able to predict problems in task performance. So just to summarize, the idea of my model of mind wandering is that mind wandering is a memory retrieval process. So when you're mind wandering, you retrieve one memory, which retrieves another and another and another, and this keeps going. However, at some point, you realize that actually you were supposed to be attending, and therefore you go back to the main task. So there's this competition between your main task, where this spotlight is represents this ability to pay attention. You pay attention to your task stimulus, and then you, in order to stay focused on the task, you have to keep checking whether you're in fact attending. And so you check whether you're attending, you check whether you're attending, but what happens in your mind is that this process gets a little tired, and therefore it becomes smaller, and then you can easily be grabbed by your mind-wandering process, which tries to creep in. So this is, of course, just a verbal model, but we can actually instantiate this in computer code. And to do this, we're making use of what's called a cognitive architecture. It's basically a simulated human mind/brain. So it was developed at Carnegie Mellon University by John Anderson, with whom we're also still collaborating. And the idea here is that it has simulations of all kinds of cognitive processes that you're using in the real world, such as, your eyes, which are, associated with brain areas in the back of your brain, the occipital cortex. So that's why we put them in this sort of schematized brain picture on the back. They're simulated hands, which are you use in a task, for example, to press buttons. There is a simulated control flow structure, which in the brain we think is associated with anterior cingulate, and so on and so forth. And all of this is controlled by the subcortical structure of the basal ganglia, which orchestrate all of those things. So we can basically write code like this. Sort of if-then rules written in a language that's based on Lisp. We might write rules like, well, if in my retrieval buffer I have a goal that is get distracted, so the distracted task, then I'm going to retrieve items from my memory store, and I'm going to empty my working memory, and then this will be followed by rules that say retrieve the next memory, and so on. So the if-then rules interact with the cognitive resources, and by doing this, I mean, what would be the point of this? Well, we are predicting what a person, a real person in a task will do. And so we can then test our model by seeing how well the responses and the response times of the simulated person agree with the responses and response times of the real person. And in this way, we can check whether our model of this reality is correct. And in this way, we can start to understand mind wandering. So that's the idea of this kind of modeling. And people have also used this kind of modeling, for example, in human-computer interaction scenarios. So you can use this to understand, for example, is this kind of a setup interface for a driving simulator? Is this going to help people stay on the road, or is this going to create lots of errors that make people go off the road? Stuff like this. So it can be fairly theoretical, like in this case, this is more basic research, or it can be much more applied. So let's, we've implemented this model, and let's actually see how we can test this. Well, in psychology, to measure mind wandering, what we do is basically the following. We give people a really boring task, and then we see how often their mind gets distracted. So the boring task in this particular case, it's called a sustained attention to response task. What happens is you see letters on the screen, O's and Q's. Whenever there is an O, you press the button. So it's like O, press the button, wait 2 seconds, another O, press the button, and then every 1 in 10, roughly, there's a Q, and you should not press the button. So yay, lots of fun, and you do this for about an hour. It's pretty mind-numbingly boring. So you're pretty guaranteed that people are going to wander off. And this is great because we want to study mind wandering, but of course then we don't know when people are mind wandering. So there's a trick to this, because every so often we just pop this question on the screen and saying, where was your attention right now? Was it on the task? Was it distracted by some sounds? Was it distracting by your rumbling stomach or other stuff? And then we can see, what's happening in behavior, what's happening in the brain just prior to that response that you give, because we know at that moment where your mind was, and we can infer that a few trials before that, your mind was still there. And so that's how we find out about mind wandering. And presumably people would do worse in the task when they're mind wandering, and that's in fact what we see. So if that's true, then how would the model this? Well, basically what happens in the model is whenever it sees an O, it sees the O, processes the O, then it will retrieve the stimulus response mapping from its memory. And either if it's supposed to press the button, then it presses the simulated button. If it's supposed to not press the button, it will not press the button. And then it will keep checking whether it's paying attention until the next stimulus comes along, is presented on the screen and processed. If there's a cue, it will then not press the button. But then, at some point, it will start to get distracted because its goal checking is impaired. So it gets distracted, sees the stimulus, but its memory is busy processing these, retrieving stuff, what happened yesterday, what will I do tomorrow, all those kind of things. So it cannot at the same time retrieve the this stimulus response mapping, so what button it's supposed to press. So then it will just press the button no matter what. So that means that whenever there's a cue and you should not press the button, actually it will press the button and make an error. So this is very simply how the model works, how we get the computer to mind wander. Okay, so we can of course implement any of those models. Is this doing it correctly? So to test this, we look at human behavior. So as I said, we put people in a cubicle and we have them do this task for an hour, and then we measure how many errors they make, how fast they are in milliseconds, and so on. And these are some of the results. So in gray is the empirical data collected by a lab in Paris, in the École Normale Supérieure, and white are the simulations, and you can see that accuracy is pretty decent. Response time, the model is a little slower, but overall it's not a terrible match. And also the response time variability, the model is within the error bars of the behavior. But most importantly, actually, when we ask this model every so often, every 90 seconds or so, where was your attention? Then actually we find that about 60% of the time the model is on task and 40% it's distracted. Now this is kind of also what we see in real humans. We find when we pop a question at you, at any moment in time, about half of the time you will say you're distracted, and about half of the time you will be on task. So this is great, and we can even ask the computer, what were you thinking about? Were you thinking about the past, the present, or the future? And it's not such a good fit, but it's still decent. Okay, so this is in general modeling the phenomenology of mind wandering. So we can actually model this. By the way, if there's any questions, anything is unclear, please raise your hands and can try to clarify this. So of course a model is, yes?
So how you model whether he's thinking future, past or present? So you ask the user whether he's doing that?
So basically what we do is we have a store of memories that the model can mind wander about, and every simulated memory has an attribute of past, present and future, and this is how we model this. So we just see what proportion of memories are retrieved are about the past or the present or the future. So it's actually not very impressive, because we can just stick in the right proportion of past, present and future memories to recreate the data. So the main thing that's actually, I think, interesting is this fraction of being on task. Yeah. And we could simulate in the same way, we could simulate things about whether these were positive or negative memories. And in fact, that's what, in another study that we did focusing on depression, that's what we actually focus on there. And there we also have a little bit more data-driven way to set the content of these memories. So, yeah. But before we do that, before we go into that study, let's see, yeah, oh yeah.
The amount of attention we pay to some task usually depends on the consequence of the task.
Right.
So is there anything that is simulated?
So yeah, the amount of attention that we pay to a task is related to, I guess, the reward that we get from that task, how interesting it is. So right now, I would say there's no mechanism to take that into account in the model, because that would make the model more complex and we don't have real data to test this. However, one of my PhD students is currently working on a model that makes use of more reinforcement learning mechanisms to actually have that be part of the model, and then we're going to manipulate reward so we can actually test this empirically. Because it is true that if we give you a lot of reward for correct responses and little reward for errors, then you get less distracted. In fact, we find another PhD student in our group, he found that when you have people do a really boring task for 2 hours, even after 2 hours, if you give people rewards, then they can improve their performance compared to the blocks where there's no reward. So this is a really powerful determinant of human behavior. Good. So let's talk a little bit about the brain, because I love the brain, and of course I've been interested in tracking mind wandering using EEG. So this is a picture from our EEG lab. We have a biosemi setup with 128 electrodes. So we get actually very nice data because these are active electrodes. So that means that in every electrode here is a little amplifier that amplifies the signal. So you get relatively clean data that's not so contaminated by movement of the wires and stuff. So the idea here is that can we find out when people mind wander on the basis of their brain waves? And although this has a long tradition of being studied, and people have even tried to come up with sort of systems that could track brain waves and be incorporated in, say, cars of truck drivers where obviously it's very dangerous to mind wander, especially at night. There's lots of accidents associated with this. So far with not great success, and I think one problem is that you need to have really good EEG data to be able to do that. And also you need to have really good methods to detect this. So we're using a combination of machine learning and good EEG signals to try to predict mind wandering. So basically what we do is we do a very similar task to the one I showed you before. Again, a sustained attention to response task. In this case, the stimuli are not O's and Q's, but they're rather words. The idea is that you press a button whenever you see a lowercase word, and you do not press a button whenever it's an uppercase word. And this is only 10% of the time. And again, every so often we ask a person, were you paying attention? On the basis of their response to this question, we can then know that the last, say, 5 trials before this question, if they say they were on task, then the last 4 or 5 trials, you could say they were on task. If they were off task, then maybe the last 4 or 5 trials, they were off task. And in this way, we can label each one of these instances, each one of these stimuli, according to whether they were on or off task. And we can then look at the brain response during those times to see whether they can in some way distinguish between being on task and being off task. So that's the general idea. Can we use some classifier to actually predict on versus off task? And the only other thing, this shouldn't be very complicated for all of you, but what the additional complication is that we don't just use the sustained attention to response task. We also use what's called a visual search task, in which you get a display. And for example, in this case, you have to look for blue circles, and then you get a display with squares and circles, and you have to see whether there's a blue circle in the display or not. So this is a nice task because it's much more visually focused. So maybe your distraction is not exactly the same. We wanted to see how task general distraction is. So that's the only thing you really need to know about this task. But other than that, it's the same. We also have these questions like, were you paying attention to the task or not? And again, on the basis of these responses, we can then label the preceding trials and use them as input for our classifier. We use a support vector machine with a radial basis function on single trial EEG. So single trial EEG is actually fairly interesting. It's a method to clean up the EEG signal by using a Mexican head wavelet, and this will look for sort of standard EEG peaks because we know that whenever you flash something at a person, then your brain does something like bloop, bloop, bloop. It goes up and down a few times. So this is a very standard EEG wave that whenever I collect EEG data, I can look for this. And so the Mexican head wavelets, the single trial EEG method, helps to sort of clean up the other stuff from the EEG and catches this. So I'm not going to go into more of this. I do have extra information if you want to ask me afterwards. But anyway, so we get the single trial EEG, and then we're trying to see how well can the support vector machine predict whether somebody is paying attention or not. We're using leave one out cross-validation, And what you can see here is that there's quite a lot of individual differences. Maybe this is also what you find in your study. So here in this study we had 17 participants, so every one of those bars is one participant, and this is prediction accuracy of our support vector machine classifier. This is 50%, this sort of red line, sorry it's a bit hard to see, but this is 50%, this is 100%. And you can see that for some participants, just no matter what you do, you're staying around 50%. For some people, you actually get pretty high. And then the other important thing to note about this is that we've tried classification for the SART, the Sustained Attention to Response task, which is this really boring task, in red. So if we're training the classifier on the Sustained Attention to Response task and we're testing it on the same task, then how well does it do? That's the red bar. And you can see this varies quite a bit, but overall it's not bad, especially this one is really good. Visual search is in green, so we're training on visual search and we're testing on visual search. You can see that actually for person 1, this is a really great one. For other people, not so much. But then we also do cool stuff, namely we're training on SART and we're testing on visual search, that's purple, and the other way around. We're training on visual search and we're testing on SART. So,
what do you mean by visual search?
So that's this task where you have to display and you have to find the blue circle, for example.
How many blue circles?
There's always one blue circle among the stimuli. So it's a little bit like you see this blue thing and you have to see, is there a blue circle among the stimuli or not? Yeah.
So the task is the number of classes are 2 here, whether he is attentive or not.
Yeah. Yeah, exactly. Yeah, so it's always attention or not attention on the basis of the response to this question, and then the instances are what happens when they see the stimuli, because if they say, yes, I was paying attention here, then this one we know they're paying attention, 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 and then we don't know anymore before that. So that's the idea. And if they say, oh, I was distracted, then here we know they're distracted. So they get labeled on the basis of their answer to this question.
How do you get these patches?
Sorry, how do we?
How do you get this blue and red circles?
So we show this on a computer screen. So there's special software to create these kind of experiments, and then you just simulate this, and the nice thing of this software is it gives millisecond accuracy in the presentation of the stimuli and the responses. Is that answering your question?
No, actually, how do you get these classes, first class and second class?
So the classes are just based on, so at this point you're asking a person, were you paying attention, or?
You are classing binary, it's a binary classifier.
Oh, right, the classifier.
How you classify these patches and how do you get these patches? Like blue one and the square one middle. What kind of apparatus you have used for I'm getting this thing through?
So what we're doing is we ignore whether this is squares or circles. That's just what the person is doing, but we're actually interested in their responses about whether they were paying attention at this moment or they're not paying attention. And then we say, okay, at this moment they're paying attention or not, that's the label. And then what we're trying to do is we're trying to predict from the EEG, we're trying to predict the label on the basis of the response. So the attention or no attention, that's the prediction. And then the accuracy is the accuracy by which we can say correctly they're paying attention at this moment or they're not. And we're making this prediction on the basis of various features of their EEG data, their brain waves. And I'll get into that in the next slide, actually. So this was just a general accuracy, but as a scientist, I actually want to know what drives this prediction. How does the SVM actually know that the person was paying attention or not, to the extent that it predicts this? So you can see that overall, this is not stellar prediction, maybe from the perspective of somebody who does machine learning classification, that you would be really focusing on 98% accuracy or something like this, but these are humans, and doing working with human data is just incredibly messy, and we only have typically a few hundred instances, even if you have a person do this for an hour. So that's the kind of reality in which we're working in this kind of context. So yeah, then if we assume that, well, this is statistically above chance, so then let's... yeah.
How many instances you collected from each subject?
So each subject was a few hundred. So I think maybe 400 or so. Yeah.
For each subject, each user?
Yeah.
Okay, so there were total 17, so 17 images.
Yeah, 7. And we did a separate classifier for every individual. Because we also tried actually a general, a cross-subject classifier, but that was not above chance, so we abandoned that. So there, and this is kind of logical, because if you look at people's brain data, they're actually wildly different. Good, so... yeah.
Did the experiment collected in the same day or in the same session, or it was collected in different sessions?
So every person just did, actually, I think we did it over 2 sessions, because we had a few hundred for the visual search task and a few hundred for the other task. So if I remember correctly, it might have been 2 sessions per individual, and they were on different days, and different people were tested obviously on different days as well. So yeah. And this is also, of course, adding to the noise in some way, but also adding to the generalization, because the cool thing is that if you can predict to someone's brain data that's collected over several days, then you know it must be something general to that person rather than something general to just that session. And then if we look at what features of the EEG are actually most helpful for making these predictions, then this is what we found. So here we're looking at how much gain in accuracy do we get from a lot of different features that we tried. So maybe for some of you for whom EEG is not so familiar, let's walk through this. So we basically focused on electrodes that were in these places. So this is an EEG kind of display. What people do is you look on top of the head, this is the nose and these are the ears. And then this is the electrode that's sort of in front, it's called FZ. This is the electrode that's sort of a little bit in the middle back, it's called PZ. And then these ones are really like here, PO7 and PO8. And these ones have been traditionally in the literature on mind wandering and attention and distraction. These have been found to be relevant. So we decided to focus on these. We decided to focus on the signals in these channels, just the raw signals, but also in alpha waves in these channels. Alpha waves are between 8 and 14 hertz roughly. And theta waves, which are between 4 and 9 or 4 to 8 hertz. So both of these waves have been thought to be related to attention. So theta in general is thought to increase when you're paying attention, and alpha is thought to decrease when you're paying attention. Or alpha goes up when your brain is idling, when it's zooming out. Okay, so then we empirically wanted to see which one is most predictive, and actually the short answer is, so here the different colors indicate the different channels that we have, and so what you can see is that the most predictive feature is the P3 in this PZ channel. It really helps a lot to determine whether somebody is paying attention. And P3 is really sort of when you have a stimulus and your brain does bloop, bloop, bloop. The P3 is something that occurs fairly late, between 300 and 500 milliseconds after the stimulus. The other thing that was quite predictive is alpha in this sort of same electrode. So those two are the most important brain waves that help you predict whether somebody is paying attention or not. So if you want to build a attention detector, probably you should focus on this one. And the cool thing though is that, as I said, this is a fairly task general thing. So on the basis of, if we train the classifier on the SART task, we can actually predict whether people are distracted on the visual search and the other way around. So this is pretty neat.
So
Yeah.
The classification task, so given this EEG signal, so what type of features you extracted? Do you remember?
So basically, the features are these kind of different peaks
Signals.
that.
These are signals.
Mm-hmm.
You extract some mean, median, power, energy, all this.
So this is just the amplitude of the signal, and in these different waves. Yeah, and also for the alpha, basically the amplitude, and this is actually, we also looked at the synchrony, so the synchrony between different channels, but basically not the variance or stuff like this, just the means essentially. Yeah. But we did look, so what you see here are lines. So when you see two numbers here, so alpha A10 to C21, that would be the alpha that goes, the synchrony between these two channels. Because some people think that actually the synchrony between channels is what determines attention. And we found that actually the synchrony, you can see it from these lines here, that's not so predictive of attention. Because this is 50%, and the higher up, the more predictive it is.
So you have these 4 points and these lines between those points.
Yeah.
What does these
lines mean? Yeah, so that's what this synchrony idea. So that basically it's a measure of how much when, say, for this line, it's how much when this one goes up, that this one also goes up. So they go up and down together, and you can measure this by looking at the consistency of the phase of these two signals. So you measure the alpha phase in this channel, and you measure the alpha phase in this channel, and then you compute the distribution of the phase differences across different moments in time. And if the phase difference is constant, then basically they are synchronized. So this is how you can measure this. Or you can measure, yeah?
You can use Laplacian montage also for this purpose?
Actually, we've not tried this, I guess. So yeah, some people have done that, but since we're already doing the single trial sort of EEG, ERP method to clean up the data, we didn't want to do too much data processing, so that's how we decided not to use Laplacian. But the Laplacian is mostly if you're interested in really knowing what part of the brain the signal comes from, because it helps to sort of get the more local signal. And that was not our main question right here. It was more like, well, what EEG feature that has been reported in the literature is most predictive of mind wandering. So, you know, different studies have said, okay, we find a significant difference in the P1, which is this initial peak that your brain makes when you see a stimulus, between paying attention and not paying attention. That's just on the basis of statistics. And we wanted to see, well, on a single trial level, can you then predict using these SVMs, and we did not find that to be predictive.
What do you mean by a separate classifier for each person?
So that means that we tested and trained the classifier just on one person's data. Yeah. Because we found that when we put all the data together in one big basket, then of course it's nice that you have more data, but then the individual differences in brain data are so large that we couldn't get any meaningful classification. So yeah.
So tested on separate persons then?
Yeah, yeah. Well, so it's the classifier is always we just divided a few hundred trials into a training set and a testing set, and yeah, this way.
So the experiment was mainly on subject-wise?
Yeah, subject-wise. Okay, so in the last 15 minutes or so, let me finish by talking about where mind wandering can go wrong, because I think this has interesting applications in mental health research, which is obviously pretty important. So we've talked just about generally getting distracted. Getting distracted is, although it has a bad reputation, actually it's not necessarily really bad. Like when you get distracted during this lecture, maybe you are thinking about some other things and it gives you a new idea for something you're working on, or new interpretation of stuff. So that's not a bad thing. But it does get bad when your mind is constantly so distracted that you cannot focus on anything else. And this is exactly what people who are suffering from depression are suffering from. So they have this process called rumination, which is a process of narrowly focused, uncontrolled, repetitive thinking that's mostly negative and self-referential. So it's thoughts like, I'm worthless, nobody likes me, I'm not contributing anything useful, that kind of stuff. So these thoughts are so persistent that people cannot focus on anything else. And as I said, it's a core symptom of depression, which is a huge mental health burden at this moment. But the interesting thing is we can look at this using the same methods of studying mind wandering that I've just talked about. So how could we model rumination? I think that a decent way to start is by just modifying the structure of the memories that the model is processing as it's mind wandering. Because if these memories are more tightly connected, then it's more difficult to get out. So basically what we did was we increased the number of memory chunks that the model was processing or walking through as it was distracted. We increased the number of ones with negative valence, and also to model the idea that it's difficult to get out of this negative valence memory, is we made these within negative, we made the negative memories more strongly connected to each other than the other memories. So once you're just caught by negative memories, it's very hard to get to this other memory that reminds you of the task. So this is very simple model manipulations. And now we're going to see how we're going to actually quantitatively set this and then make new predictions, because that's really what a model is supposed to do, right? It's supposed to not just fit the data, but actually make new testable predictions. So we had used a very cool method to actually set the structure of the memory, so determine how many memories, exactly what the connection strength should be, by a new kind of data that's called experience sampling. So this is made available by the common occurrence that people have a smartphone. So what we can do is make use of this smartphone and prompt people maybe 5 to 10 times a day with questions like, what were you thinking of? How are you feeling? Are you able to concentrate? Those kind of questions. So this is called experience sampling. And they give an impression of participants thinking over the course of their real life. So as you might have noticed, all the stuff I was talking about before is we dump people in a cubicle and we just look at what they do in the lab, but this is very artificial. What are they really doing in their real life? That's what we want to know here. So in this huge data set that I got from some colleagues, they looked at 129 depressed people and 212 controls that answered brief questionnaires 10 times a day for 5 to 6 days. So this is pretty nice. So we know for these 10 people, these like 300 plus people, what they were thinking of. So let's just look at some of the data and how well the model can at least qualitatively model this, because it's not exactly the kind of data that are models, but still we should be able to determine how many memories, positive and negative memories the model has on the basis of these data. So in the left, we're going to show experience sampling data. So that's the empirical data from the smartphones on the basis of these questionnaires. And in the right, we look at the model and we look at positive mood and negative mood. So positive mood. And actually, we're also going to see yellow is control and blue is depressed people. So here you can see actually depressed people show a wild difference from normal people. This is how often, this is a histogram of how often they report positive mood. So on a scale from 1 to 7, how happy do you feel, more or less? You can see that the control people tend to score 5 or 6. Depressed people just a 1 or a 2. So this is a very clear difference between depressed and happy people. And our model sort of qualitatively captures this. Again, as I said, the model is not designed to give 1 through 7 answers, so we've just used the summed activation of the different memories as a proxy, so this is why it's not giving exactly the same kind of shape of the histogram, but at least it gives the nice shift between depressed and happy people. And the opposite for how unhappy sort of do you feel? This is a combination of different questions that are sort of negative moods, and you can see that the depressed people overall score higher than the control people, and same for our model. So this is, well, very rough data. We can also go in a little bit more into what actual moods do people report, and for the empirical data we find that healthy people, they report being more cheerful and content. That's these two bars. So you can see that the yellow is bigger than the blue, so control is bigger than depressed. For negative moods, like feeling down, insecure, and suspicious, we can see it's basically the opposite, and the depressed people feel more like that. And this is what we find in our model. You might also notice that there's one notable difference in the shape, where in the experience sampling data, there's this weird thing that depressed people score the same thing on cheerful, content, down, insecure, and suspicious, whereas the control people are actually report less negative, whereas, so it's as if the control people are biased towards positive, whereas normally what you find in real data is more that depressed people have a bias towards negative, and that's actually what our model is modeling, but it's not in the data. So we think actually it's a weird thing in these data.
How did you construct that model?
So this is basically just changing the valence of the memories, similar to the past, present, and future, but now setting the number of down, insecure, suspicious, those kind of 5 valences on the basis of what we found in the experience sampling data. So this was really trying to set that proportion. We did sort of a grid search of different models with different numbers of those different kinds of memories to try to reproduce these data as much as possible. So this is more or less a data fitting exercise, but we're going to soon go to the interesting part, namely to say, okay, if we fit this structure on the basis of people's responses, then can this actually predict problems in concentration?
Could you please explain about the collection of the data? How did you collect the data?
So the data were collected by my colleagues, and basically what happened is that people got a question on their smartphone 10 times a day, like different questions. How happy do you feel on a scale from 1 to 7? How do you feel you can concentrate? How insecure do you feel? So all of these were literally the responses to one of these questions on a scale from 1 to 7. So you get basically a whole set of numbers, well, 10 reports of people times 5 or 6 days, and then people were convinced to do this by giving them a report of their moods over days, which they found quite attractive. So yeah, you're just literally asking people.
So, and the models are basically constructed based on the collection of data. So using
Well,
the mean of the samples.
Not quite literally. So the model has a collection of memories that it sort of retrieves when it's mind wandering. So it has maybe 30 memory chunks in its simulated memory. And then what we manipulate is the number of positive and negative or down, insecure, and suspicious memories. And then we have the model run through this. We simulate, the model mind wandering for like an hour, and then we just count how many positive or how many down, insecure, suspicious, all of those memories does it actually retrieve, which then affects, so what I've actually glossed over in this is that the memory system is really based on a lot of behavioral data, and models the idea that if you retrieve a memory, it gets strengthened. If you don't retrieve a memory for a while, it actually decays in its strength. So all of those principles are incorporated. So it's not like exactly, you can easily transfer the frequencies that you observe in the experience sampling directly to the model. So this is why we did a grid search on how many memories should be down, insecure, and suspicious, and what should be the strength of the connections. And then we found the one that was sort of fitting best. So it's a bit more complex than that. But the nice thing of this slightly complex model is that we can also then have it do a task and see, you know, how often does it get distracted with this memory structure. And we have it do the same task that I already mentioned. We would, of course, predict that people, if they have trouble concentrating, that they get more distracted and that they are doing worse. So they make more errors, they are slower in their response time. Basically, very briefly, this is what we found. So if we look at the accuracy, then the control model, the healthy model, has a higher accuracy than the depressed model in blue. There was not really that much of a difference, only tiny difference in how much the simulated model was on task. So the controls model was slightly more on task than the depressed model. And the depressed model was also slightly more variable in its response times than the control model. Yeah.
How are you able to simulate the memories in a model?
So this is basically simulating the memories in a model is basically, well, that's part of the architecture. So the architecture has, you can just define the number of memory chunks that it has, and you can define a starting value of how active they are, and then the equations underlying this model then describe the decay of these memories based on how long the time has been and how often they have been used. So if they get used more, then their activation becomes bumped up, and then when they're not used, their activation sort of decays, and like that.
What defines their usage?
What defines their usage? It's basically whenever they're retrieved, that's when a memory is used. So if the model is mind-wandering, it picks the most active chunk from its memory, and that's when it's used. And then you add another, basically, usage to its record, and it gets this bump in activation.
And how is the model, independent to switch to mind-wandering and being attentive?
So how does the model switch from between mind-wandering and attention? This is on the basis of the activation of goals. So it also has two, you could say, memories that define its goals. One is the mind-wandering goal and one is the task goal. And initially, the task goal is a bit more active. That's what I set in the settings of the model. But then also these goals decay over time. So this the task goal sort of becomes less active, and then the mind-wandering goal becomes more active. And as soon as this becomes more active, then you switch to mind-wandering. But then the mind-wandering goal again decays, and the normal task goal gets a chance to be bumped up again, also by some random noise. So this is how this dynamic sort of, yeah.
This kind of pattern is already structured, like it will switch for initial time it will decay, and in certain time it will switch to the attentive mode. So we have structured it already.
So the decay times are determined by the architecture, so I have no say on this. So this is on the basis of previous research on memory, how this works. So the dynamics is mostly set by these equations that are general, determined by other data. Yeah, good questions, thank you. So I guess let me finish by showing that actually these are model predictions. Where we did, just on the basis of setting the model structure by using this experience sampling data, so these data basically, we then give the model a task and make these predictions, and then we actually ran the experiment with some people who had a tendency towards depression, and we looked at how well they were, what their accuracy was, and we found that basically that people who were high on rumination, that they, so people who had this tendency towards depression, that they did worse on the task than people who had less of a tendency towards depression. These were not fully blown depressed people, because that's really hard to get. You have to get special ethical permission, so we just used normal students. But we did find that people who are, actually the labels are incorrect, I'm now just noticing. So these are, the yellow ones are low ruminative and the blue ones are high ruminative. And we can basically see that people who have a tendency towards depression, they just do worse. And these are two task conditions that I'm going to skip just in the interest of time. So their data are at least somewhat in line. It was not a huge effect, but it did show up, so that's very nice. And yeah, we've also used similar models to investigate mindfulness, but again, I'm going to skip this for now and just switch to the conclusions, and we can talk about it more afterwards if you want to. So I asked this question, why should computers mind wander? And I think why computers should mind wander, why I've tried to create a mind-wandering computer. Of course, I don't really believe that the computer may be really mind-wandering, but at least simulating these cognitive processes is because they help us better understand what people do when they're mind-wandering. It allows us to, computers allow us also to develop the tools to track mind-wandering, so this is a slightly different approach where we use machine learning to try to predict on the basis of people's brain waves when they were mind-wandering. And then actually in a separate line of research, I'm also working on applying these same techniques to study the effects of mindfulness on cognition. And in the slide that I just skipped over, we basically were able to predict improvement on an attention task after the computer was practicing mindfulness for about several hours. Then it got better on a slow attention task, and this was similar to what real humans had been doing as well. So that's it for now. I'm happy to take any further questions. Yes.
Ma'am, can we use this type of models for like predicting behaviors, kind of like suicidal tendencies or depressions, or like if people like mind wander, will they be like influenced by something?
Yeah, so that's the idea. We can use, so the question was, can we use these models to predict behavior in different situations? And that's the idea. This is basically some very simple models of mind wandering in a very constrained task situation. But the nice thing of using this cognitive architecture is that in principle, you could put the same mind wandering model in a different task. So now I have one student who is working on a different attention task, which is still quite constrained. But in principle, you could also put it in a driving simulator and see what it does. And because we've already fixed sort of the structure of the mind wandering and sort of there's not that many parameters we change from their defaults, but to the extent that we did, we've already fixed this, and then we can transfer it to a different situation. And we can also manipulate parts of this task. So we can, for example, have the stimuli come much closer together in time and see how that affects mind wandering, where you would predict that mind wandering would decrease if the task were a little bit more busy, or you could change the reward like you were proposing. So yeah, that's exactly what the idea is here.
Any more questions?
Yes?
To capture the subjectivity of the domain itself, can we develop an egocentric model rather than a general model?
An egocentric model? You mean an individualized model that describes an individual person?
Yeah, the equations, the variables of the equations will depend on them.
Oh, right. I think in principle this is definitely possible. I've not yet ventured into trying to build an individual specific model, but in principle you could set, for example, the activation of the mind-wandering goal at the beginning. You could set that on the basis of an individual's performance. Actually, this is one of the plans we have with the PhD student who is now improving on the model with reinforcement learning, is that maybe we're going to do a separate pre-task in which we might set the person's goal, executive function, how well they're able to trade off goals, and then use that to set that parameter and see how that affects the model's performance. So yeah, that's definitely possible, but it's computationally a lot more difficult because you have less stable data essentially. So yeah, so I'm curious to see how that's going to work.
Related to first model,
Yeah.
MW model, mind wandering model,
Yeah.
you define two variables, that is sort and base. Can you elaborate it?
Oh, right. So the SART is this sustained attention to response task. Actually, let's see whether you can go back to. So SART is, sorry, this is probably like my, the psychologists speak that psychologists are very familiar with those kind of concepts. So the SART is sustained attention to response task, and it's this task where every 1.5 to 2 seconds you see a word and you just have to press a button, except when the word is in uppercase. So in this case, you press a button here, you press a button here, you do not press a button here. That's the SART. The VS is visual search, and it is this task where you see this display with multiple shapes, and you have to say whether the target shape, in this case a blue circle, is among the different shapes that you see, yes or no. And so half of the time it's part of these shapes and half of the time it's not. So that's just, it's different kind of things that people have to do in their cubicle. Yes?
What does SP and NT mean there? SP is target and NT is output.
Right, so SP means search, I don't know actually what it means. It's basically the search panel, that's it. So with target means that the circle that you're supposed to scan for was actually in the panel, and this is a search panel without a target, so there is no circle in there. So that's the two possible conditions that people encounter when they do this.
NT go stimulus.
Sorry?
NT go stimulus, you have written there.
Yeah, NT go stimulus. That means non-target go stimulus. So so this is again sort of, sorry, this is psychologist speak. So you have targets and non-targets. Basically, in this kind of a task, the target is the most difficult one, which is when you should not press the button. And this means when you press the button. So non-target and go is exactly the same, because go means you press the button and no-go means you do not press the button. Yes?
Like EEG, we are using in many research papers, like in last 3 to 4 years. Researchers are using EEG in neuromarketing.
Mm-hmm. Yeah.
Any scope in EEG e-commerce related?
Well, I guess
Because Walmart is trying
to
improve their
use
business, and Amazon India also.
Right. Yeah. I'm honestly not sure how useful EEG data are, given the kind of data that you get with these commercial headsets, like the Emotive or those kind of things, the Muse. So I think probably if I were these kind of companies doing neuromarketing, I would just really bet on eye movements and pupil size. I've actually worked with a student on these kind of questions, like to what extent can we predict what food a person is going to choose if they had to decide between different snack foods, and on the basis of the patterns of their eyes, and you can actually track those with webcams nowadays. So I think that's much more feasible. You get much better data, and you can actually get a lot of data on the basis of people's eyes. And actually in a work of another PhD student, we found that we can predict to some extent whether people are paying attention also on the basis of pupil size. Now that was with a proper eye tracker, because pupil size is still a bit hard to do with webcams, but it probably, if you have good computational tools, you might be able to do it. And I think the combination of pupil size and where a person is looking and maybe how variable their gaze is, you can find out both about their attention and their choices, their interests, much more than with EEG. That would be my bet. Yeah, because I think EEG has also a lot of noise, as you saw here, so it's quite hard to do those things.
So, any more questions?
One more.
In your work, you have stated that you have sampled the population in which there are people in control and there are people who are depressed.
Yeah.
Blue and yellow.
Yeah.
How was it categorized? Certain person is depressed and certain person is
Right.
in control.
So the people in that study, I think they were diagnosed as clinically depressed. So this was, the study was done at a hospital, a University Medical Center Groningen, I think also University Medical Center Maastricht, so two university hospitals. So they were diagnosed on the basis of interviews, questionnaires by a clinical psychologist. And then they were invited to take part of this study, in this study. Yeah.
The people in control were too examined for that?
So they were just recruited from the general population, and it's basically they were allowed to participate if they self-reported that they did not suffer from any mental disorder. So of course you're never completely sure, but you assume that most people will be honest on this. And
voluntary, actually.
yeah, it was, well, I think it was completely voluntary, and people were just motivated by this report on their own data. So they got some graphs on their own data at the end of the study, and apparently this was a really effective way to motivate people to take part in these studies. Normally, when we do these studies, actually just for your reference, the ones in the lab, these very boring tasks, we convince people to do that by giving them some modest participation fee. So we pay them typically, I think, about €7 per hour, which is not a lot. It's less than the minimum wage, I think, in the Netherlands. But it's still, students will be often happy to, make some cash on the basis of.
Giving rewards, even if a person who is depressed, in sake of rewards, he would come to your service in that scenario. Is it not possible?
It is definitely possible, but if we look at the data, I think the differences between the depressed and healthy people look quite dramatic. So my guess is that there's at least not many depressed people among the control group. So yeah.
One last question. When you use the word model,
Yeah.
there is some framework of the model and some mathematical equations there. So can you find somewhere in this slide?
Sorry, can you? Yeah? This ACT-R model, right? Yeah.
Sure. So can you find the framework of the model?
Right, so
Some structure, so some mathematical equations. That is the term coming into pictures, the model what you are using here.
Right. So I don't have a slide or some real overview of these different equations, but it's basically mostly a simple exponential. That's the decay of each individual memory chunk. That's the main equation that underlies this, and this decay is then bumped up by every time a memory gets used in the model. Then there's also I think that's really the only equation. The rest is more algorithmic. Like if we stick something in the working memory, then it also gets a bit more active, and it takes a certain amount of time. Every if-then rule that's fired takes 50 milliseconds. So those kind of constants are part of the model, but it's not exactly equations. It's more like algorithm. And if you want to find out more, then I guess this, just Google ACT-R, and there's a huge website on it which has all the proper documentation. Let's see, and this, I think this is the original reference. So, any work by John Anderson from CMU, that also explains the more details about this model. Yeah.
I think there might be a lot of questions. This is a very interesting topic, and Professor Marieke is an expert in this area, and she has worked for a long time, and the lecture was also very interesting. So hopefully you have all enjoyed. So let's thanks again. So we have lots of questions. So we'll be discussing with you. So Professor Marieke will be there with us today, tomorrow, and she will be leaving day after tomorrow in the morning. So if you have any questions, you can drop a mail, or you can meet her anytime before that. So.
And thank you so much for your wonderful questions. They were great insights.
So small token of appreciations from IIT.
Wow, thank you very much. Great. Wonderful.
Okay, thank you very much. So I just lastly I would like to thank the IIT Roorkee for organizing such a wonderful lectures here today. And I also would like to thank Professor Anil Gauri Shetty. He is the professor in charge of this institute lectures. So he has organized all these travels and all the arrangements for bringing her from Mumbai to IIT Roorkee through Dehradun, and so thanks again. All the faculties and all the ICC staffs who are supporting these lecture rooms and also the video conference, video recording groups, everyone, and all the participants again for coming here.
Yeah,
Thanks again. And so hope if you have any discussion, we'll be discussing in offline.